Welcome to Ask and Learn.
We are given a regular grammar, and we are asked to construct a non-deterministic finite state automaton that recognizes the language generated by this grammar. So we're given a regular grammar G, which is equal to the four-tuple VTSP where V is 0, 1 SAB, T is 0, 1. Of course, S is the starts, and then in part A, we're given that the set of productions is we have that S can be replaced by 0A, S can be replaced by 1B, A can be replaced by 0, B can be replaced by 0, so first we have the initial state S0, which corresponds to S, and then next we'll draw an arrow with input 0 from S0 to the state SA. Where SA is the state which corresponds to A, and this represents the production S can be replaced by 0A. Next, draw an arrow with input 1 from S0 to the state SB. Where SB is the state corresponding to B, and this represents that S can be replaced by 1B. And finally, draw arrows with input 0 from SA and SB to F. Sorry, F instead of SF. This is a final state, F, and this represents the production A can be replaced by 0 and B can be replaced by 0, and F is the final state. Now in part B, we're given the same grammar except now the set of productions P, well, this consists of S can be replaced by 1A, S can be replaced by 0, S can be replaced by the empty string, A can be replaced by 0B, B can be replaced by 1B, and B can be replaced by 1. Now first draw start state S0 corresponding to S. Since one of the production rules is that S can be replaced by lambda, which is the empty string, it follows that S0 needs to be a final state. Now, let F be the final state for non-empty strings. Draw an arrow with input 1 from S0 to SA. SA represents the state corresponding to A, and this represents the production that S can be replaced by 1A. Now we can also draw an arrow with input 0 from S0 to F. Because this represents the production that says that S can be replaced by 0, which is a terminal symbol. Now draw an arrow with input 0 from SA to SB. And the input for this arrow is 0. So this is an arrow with input 0 from SA to SB. This represents that A can be replaced by 0B. Now we'll add a loop with label 1 to the state SB. This represents the production that B can be replaced with 1B. And finally, draw an arrow with input 1 from SB to F. This represents the production that B can be replaced by the terminal symbol 1. This concludes the construction of the machine. Now in part C, we're given the same grammar, except now the productions are S can be replaced by 1B, we see that S can be replaced by 0 and A can be replaced by 1A. A can be replaced by 0B and A can be replaced by 1. A can be replaced by 0 and B can be replaced by 1. And first, we're going to draw an initial state, S0. And this, of course, corresponds to the non-terminal symbol S. And we have that since S can be replaced by lambda is not one of the productions, it follows that S0 is a non-final state. Now, let F be the only final state. Now draw an arrow with input 1 from S0 to SB. And this represents that S can be replaced by 1B. Now we'll also draw an arrow from S0 to F. And this arrow has an input of 0. And this represents that S can be replaced by 0, which is a terminal symbol. Now draw an arrow from SA to itself. In other words, draw a loop at SA with an input of 1. This represents that A can be replaced by 1A. And we'll draw an arrow with a label of 0 from SA to SB, where SB corresponds to B, and we see that this represents that A can be replaced by 0B. And we'll also draw an arrow from SA to F with input 1. This represents that A can be replaced by 1, which is a terminal symbol. And we can also draw, well, another arrow. So we'll actually draw 2 arrows with inputs 0 and 1 from SA to F. So we represented before with the 0 that A can be replaced by 0, and now with the 1, this means that A can be replaced by 1, which is also terminal. And finally, we can draw an arrow with a label of 1 from SB to F. And this represents that B can be replaced with 1, which is a terminal symbol. And this concludes the